Hi and welcome to another lesson about memory. This time we are going to talk about the load effective address instruction. Objectives of this lesson. We will study the load effective address instruction. Let's begin. LEA stands for load effective address. The syntax of this instruction is something like this. LEA, then the dest argument, and finally we have a special argument which must have brackets, and inside those brackets there is some kind of expression. Basically, LEA calculates the expression and stores the result inside dest. Something important to know about LEA, it doesn't actually access any memory. It only calculates the resulting address. Maybe when you have looked at the move and the add instructions and so on that we have seen in previous lessons with the bracket syntax, maybe you were wondering how could you utilize the power of the bracket syntax to your advantage and maybe use it outside the realm of memory. Maybe you just wanted to calculate things using that bracket syntax, but you couldn't because you could only use it to reference memory. Well, the load effective address instruction actually gives you the power of the bracket syntax without having to reference memory. That's the power of the load effective address. It gives you the ability to calculate strange expressions with the bracket syntax, but you don't have to read or write to memory. Basically, LEA is usually used to calculate addresses, but you could use it to do any other calculations that you want. Another strange thing about this instruction is that it doesn't change the flags register. Some limitation that you should know about the dest argument is that it must be a register. It cannot be anything else. For example, you can't put a memory expression here or maybe something different. It has to be a register. Let's look at some examples. The first one, load effective address EAX plus 1. This instruction is going to add 1 to EAX and store the result inside EAX. As we can see, it didn't reference any memory. It just calculated this expression and store the result inside this argument, which is EAX. Another example, load effective address ESI EAX plus 2 times EDX. Basically, this instruction just calculates this expression, EAX plus 2 times EDX, and stores the result inside ESI. The third example, load effective address DI EAX plus 2 times EDX plus 5. I chose here DI because I wanted to show you something. DI is shorter than ESI, for example. DI is of size 16 bits. You might be wondering what happens if the expression on the right cannot fit into 16 bits. Well, there is a simple explanation. If the result here in this expression is too large, it is wrapped around, which means that only the lowest 16 bits are taken. Maybe in another formulation, we actually calculate this expression, EAX plus twice EDX plus 5, and then we calculate modulo 2 to the power of 16. Only then we store the result into DI. The same applies for the previous instruction, this one and this one. If the result here, for example, is too large, it is wrapped around and only the lowest 32 bits are stored into ESI. The other bits are just discarded. As usual, let's look at some invalid syntax, things that you should not use in your code because it will just not assemble. The first example, LEA EAX inside brackets, and then EAX plus 1 inside brackets. this is not going to work because we've already talked about it. The dest argument or the left argument has to be a register. And here it is not a register, it is a memory location. Therefore, this instruction is invalid. There is no such instruction and it will not assemble. Another example for such an invalid instruction. LEA, ECX, EDX. This time the problem is with the EDX, the second argument. In LEA instruction, the second argument has to be an expression inside brackets. And this is not the case here. So this instruction is invalid and it will not assemble. So don't use those two examples. The expression in brackets is just like any expression in brackets that we have seen before. For example, we can use the brackets syntax with the move instruction or maybe with the add or the end instruction. The same syntax applies here in the LEA instruction. It is exactly the same syntax. However, LEA is special because no access to memory is done, although there are brackets. I think it might be the only instruction that has brackets but doesn't access memory. Usually when there are brackets, there is access to memory. But LEA is a special case. There are brackets but no access to memory. And I want to remind you that the expression that you use inside the brackets cannot be too complex. For example, this is about as complex as it can get. We usually have maximum of 2 registers. Maybe one of them can be multiplied by a constant, usually a small constant, and you can add or subtract some other small constant. And this is about it. You can't do, for example, ESI times ECX. For the most part, you can't really get more complex than that in the bracket syntax. You can't, for example, do something like ESI times ECX. This is not going to work. You can only multiply by a constant and add some simple things. That's about it. Let's look at the first example. We can see 2 pieces of code which only differ in this instruction and this instruction. LEA here and move here. And the same for the second instruction. LEA and move. We can see that everything else is mostly the same. Let's take a look at the code. We can see that there are 2 sections here. The first one is the data section, which as expected contains data, and the other one contains code. The data section consists of 2 structures, 2 constructs. The first construct is called nums, and it is actually 100 dwords of this value, 1, 2, 3, 4, 5, 6, 7, 8. snums is another construct which consists of 100 words which have this value, AB, AB. Just to make sure we are on the same page, let's repeat what we have seen here. The first one has 100 hex elements, where each element is of size 4 bytes. The second construct, called snums, consists of 100 hex elements, where each element is of size 2 bytes. Let's move on with the code. We first move the label nums, which actually contains the address of this data, into ESI, and the label snums into EDI. Basically, at this point, ESI points here, and EDI points here. Now we read a value from the console using the read hex function. Now we have 2 LEA instructions, and this is where the interesting part happens. This LEA instruction gets the address of dword number EAX. We want to get element number EAX from the nums array. How can we do it? we take ESI, which is the base, the beginning of the nums construct, or the nums array, and we add it 4 times EAX. Which means that finally EDX is going to contain exactly the address of the word number EAX inside the nums construct. If we want the address of element number EAX, this is how to calculate it. We take the base and add 4 times EAX. Basically, this kind of code or instruction is what gives the construct nums its meaning. Without this instruction, the construct nums is just some kind of a boring set of bytes. It doesn't really mean anything. But when you do something like this, it gets the meaning. Now that you do this kind of instruction, it has a meaning of an array of D words. At least this is how I think about things. I think that the code gives meaning to the data. Let's move on to the next LEA instruction. This one is related to the snums construct. We can know it because it uses the EDI as a base address, and EDI contains snums. So this time we want to take element number EAX from the snums construct. This is why we multiply by 2 instead of by 4. In the first case, we multiplied by 4 because each element was of size 4 bytes. But in the second case of snums, every element is of size 2 bytes because every element is a word. Therefore, we multiply by 2. I just want to mention that eventually EDX and EBX contain addresses. Those two registers are going to contain addresses, which we cannot guess at this point from looking at the code. There will probably be some large numbers, and basically we might be able to guess the difference between the value that will be inside EDX and EBX, but we can't know the values before we assemble the program and run it. We can only guess. I want to take a look at the parallel code here, which contains the move instruction instead of the LEA instruction. And I want to discuss the difference. Everything is exactly the same, so the only difference are those two instructions. It is easy to mistake because LEA and move have such similar syntax. Look, there is really no difference in the syntax besides of the name of the instruction. But here, in this example, LEA doesn't access the memory, it just calculates an address. This is just a calculation. However, here something absolutely different happens. Here, we really get the D word in this address. We really get D word number EAX. Here we access the memory. Also in this move instruction, we access the memory. So in the first case, we actually take element number EAX from the nums construct, which means that we read from the memory D word number EAX from the nums construct. By the way, the result is going to be, as expected, 1, 2, 3, 4, 5, 6, 7, 8 in base 16. This is what EDX is going to contain. In the second case, we get word number EAX from the snums construct. And as expected, the result is going to be ABAB in base 16. So those are two different examples. On the left, we are going to get the address. But on the right, we actually read the data from memory. Here we get the actual contents of the data, of the memory, and here we only have the address. Let's look at another example. Adding numbers from 1 to 100. This example emphasizes that the LEA instruction doesn't change the flags register, so we cannot rely on this instruction to check the flags later. This is pretty much a very simple example. We've seen so many examples of this type, but this time there is a mistake in the code. Let's look at the code. First we initialize ECX to be 100 because we are going to do 100 iterations. And then we initialize EDX to be 0. EDX is actually going to contain the sum. We can see here in the loop that in every iteration we add ECX into EDX. So EDX is really the sum of the numbers. We also see that ECX is decreased by 1 in every iteration, in a very strange way, using the LEA instruction. The mistake is somewhere here in the combination between LEA and jump node 0. What is the problem? We want to identify the exact point where ECX equals 0. So the naive thing to do is to use the jump node 0 instruction here. But there is a problem. The LEA instruction doesn't change the flags. So the jump node 0 actually relates to the add instruction. The add instruction here is the last one that really affected the flags. So we don't really check 100 iterations here. We do something different. We add until EDX is 0 modulo 2 to the power of 32, which is absolutely different. It is a different thing. So this is not the behavior that we wanted to have. So don't do this. Don't rely on the LEA instruction to change the flags, because it is not going to change the flags. Let's look at an alternative piece of code that actually does the job, that does the addition of 1, 2, 3 and until 100. The only difference is that we added this instruction, test ECX ECX. LEA doesn't change the flags, but test does change the flags. So we can just test ECX with itself and then check if the result was 0 or not 0. This is an important thing to remember. LEA doesn't change the flags register. Another example, we can use LEA to save instructions. This is one of the reasons that I really like this instruction. At least personally, I really like it. Let's look at those two pieces of code. I will begin with the one on the right because it is a bit easier to read. We want to calculate this expression, ECX plus 4 times EDX plus 5, and assign the result into ESI. This is how we would have done it if we didn't have the LEA instruction, which would have been pretty sad, I must admit. We first copy ECX into ESI, then in some kind of an independent manner we multiply EDX by 4 using the shift left instruction. We shift left in 2 positions. Then we add the result of the multiplication to ESI. Finally we add 5 to ESI and we get the wanted result. Basically those two pieces of code are equivalent, besides the fact that the code on the left is going to change the flags register, but the code on the right doesn't. It doesn't change the flags. For the most part you won't care about this at all, but if you do, you have to be careful. Summary of what we have seen. The LEA instructions allow to calculate addresses easily. LEA doesn't actually access memory. It only calculates addresses. The LEA instruction doesn't change the flags register. This is about what I wanted to tell you about LEA. See you on the next lesson.